Thank you guys for making your time here. And today we're going to talk about building a scalable compute workflow for quant research with Ray on Kubernetes. So who am I? I'm a senior quant developer at a quant trading firm called Chicago Trading Company. I'm on a systematic trading equity team. And this is my second year at Ray Summit. I really enjoyed my last year, so I hope you guys are having fun this year. Today we're going to learn first, why I think Ray can play a really important role in quant research. I know it's it's all about AI, large language models these days, but let's delve into something new. And I want to share some battle-tested practices running in the quant workflows with Ray on Kubernetes. Okay, so let's look at one flavor of quant research and trading. So let's say we want to trade stocks, right? What we want to do is to find as much data as we can. It can be prices data, it can be news data, it can be social media data, it can be credit card alternative data sets. And then we use them and build like machine learning prediction models to predict the forward returns, which really means just predict the prices. Then we build a portfolio and then we trade it on the exchanges, yada yada, no one cares. So today, what we're going to focus is this light blue box. Because what this means is you want to gather like 10 or 20 years of data, lots of them every 1 minute, and then you really want to like train a large model to capture all of these like relationships, linear or nonlinear. So as you can see here, it's hinted like it's a lot. So let's formally define our goal. So our goal is we want to support a bunch of very well-defined research jobs that leverage this data and do compute on them, right? These jobs can be feature generation, it can be the prediction, it can be backtest, which is like run your portfolio over a long history throughout time. It can be reporting and P&L attribution. So what it means for compute is, let's say we want to have 100K CPUs concurrently running to support, like say, a dozen of users. So yeah, in quant, each user get a lot of CPUs. And then we want hybrid compute because we want to build machine learning, deep learning, or like NLP models. And to give a rough size of data, I think this is a very modest estimation, but over 100 terabytes compressed data. And I want to say it's hot data. So it means that like some firms have really big data, but like you always need like the last 6 months. In quant, you always need everything throughout history because you want to run the jobs on long history. So why Ray is a great fit? So first of all, Ray is a Python-first framework, and Python is an incredibly powerful language in quant research. And building on top of that, quants also use a library called NumPy for numerical operations a lot, and Ray has a really specialized support for zero copy of NumPy arrays, which is super nice. And the third is Ray is very good for CPU and GPU hybrid workloads. And the fourth is, like it's very easy to actually deploy Ray in research and production thanks to Kubernetes. So Ray has an array of toolbox, all of them very useful. But today we're going to focus on Ray job because as I hinted earlier, quants wants to run certain types of jobs and do their research. So let's say you want to run a job. What do you want to do? You want to do the most basic thing, which is these three little people here. You just want to run Python, run backtest, and then you start to run the job on a cluster, right? Everything else is taken care of. But let's break it down to what happens behind the scenes. So first of all, you run the entry point. Secondly, what the workflow should happen is it should package your local workspace into a Docker image and push it to somewhere, right? And then you invoke a Ray job that will just pull this image down and start to run it with a predefined resource definition. And then you want to know if the job dies or is it successful, so you just pull the job status. You can do it from the same terminal. So we actually tried this workflow in our previous version, and we call it Rayflow 1.0, which is that simple. So let's look at its pros and cons. Want to highlight the pros of a very fast R&D loop. I think you guys all heard about the dependency hell, blah, 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 like in today's keynote. And that's very key here, is we just snapshot the workspace of a researcher that comes with any code he or she just wrote like 2 or 3 seconds ago and build an image from it. So this is very nice. Also, the time to market is fast because like it takes literally like 1 hour to set up. The cons are big too. First of all, in our previous example, we only have one cluster. And remember, our design goal is to support a dozen of researchers on like a dozen of like Kubernetes clusters. A second come with that is we don't have redundancy, right? So like if everyone is on the same cluster, what if we need to do maintenance on it? And the third that is very, very important is the scalability has no guarantee because we do it in a fire and forget fashion, right? We just submit a job and then like just pray. So spot eviction, I want to highlight, is a very important issue in compute jobs because like it's so much cheaper, we have to use them, but it means that the cloud service provider can take it away anytime they want. So we need to build some stability. So now this is the V2 architecture of what's currently like running right now in my team. So you can still see the 3 little like people here, but you notice 2 boxes of them. So they are like, these can be 2 research teams. It can be like just 2 user groups within one research team. And you can see they go through one small light purple box, and then go to the 2 cluster representation. So the small eclipse there are the jobs. Right? And we're going to dive into this in details. So what this little purple box is really like a broker. So instead of researchers just submit the jobs directly onto the Kubernetes cluster, they are going to submit to a broker, and the broker is going to route the job to the predefined clusters for these researchers, right? So you can route to that one, and this group gets routes to that one. So why this is a good design? This allows you to do canary deployment because you can temporarily shift some researchers from one cluster to another cluster. You can also let you scale horizontally very easily. Think about more researchers coming in, more training desks coming in. You are just going to add another box here, and it still goes through the little purple box, and everything is taken care of. So this little purple box really has a stateless design, so it's not really a single point of failure. And like I said, spot eviction is a very bad thing to happen. And what you want to do is to interact with the job. So there are 2 types of interaction you can do. The first is quite trivial. It's like save the job logs and notify the user job. So what we built, the job status. So what we built is something called a controller. It basically loops through every jobs that's currently running in all the clusters we have, and then do a bunch of things like notifying the user. But we also wanted to interact with jobs in a non-trivial way. That's what we call a policy and its handlers. So what does a policy look like, and why we need a policy? We want to be able to characterize jobs into 2 types. There are only 2 types of jobs: the fast jobs and slow jobs. Fast, like a common definition is like faster than like 2 hours. We want the job to be idempotent, so we can just like naively retry it, and eventually it will just finish. For really slow jobs or job that's very expensive to run, we want to build something that's resumable, meaning like we want to build checkpoints into the jobs. This is a must. I'm sure if you're familiar with like training ML models or like use retrain, like you already are using it. And then let's look at a real example here. So this policy this message is basically told to the user by the controller that your job running into a failed status. Sorry about that. But then because you assign a policy with it, and the policy is let's retry this job with increased memory, and let's retry once, and let's increase the memory per core by 2. And of course, it inherently knows that whether it's an idempotent job or it's a job that already has a resumable checkpoint built from it. And then you can see, your new job, which is a child of the failed job, succeed after increasing the memories. So let's review the V2 architecture. I think the pros is really our design goal. So we have multi-cluster scale. Like you can scale to 100K CPUs concurrently without any problem. And you have canary deployment, which is like good software engineering practices. And the second is these policies are really, really customizable. I want to give one example. So because Ray job submission client give you a tail of the logs, so you can say, hey, let me tell this job with these logs. If I see this string, I need to do something really customized, really ad hoc. So I think this is a very good design, and it allows very customized things. The cons is it's pretty obvious. You have more services to manage. You have one purple box sitting in the middle of everything, and then per Kubernetes cluster, you have kind of like daemon service running and talk to it to handle the things, handle the jobs running on that specific cluster. Okay, so I want to talk about the lessons that I learned. So personally, because we already achieved the canary deployment, I highly recommend aggressively upgrade your Ray and Kubernetes version. I find them, like right now they're doing weekly releases. I find them do a really good plan, doing a good job of testing the releases. But it's also because the architecture we have is so easy to roll back. The second is a trick I want to share that is very common in quant research, is like some users, like they're just comfortable writing their own stuff, like they might not be comfortable to migrate to Ray, but any compute can be expressed as a DAG, and any DAG can be represented by an intermediate representation. So what you can do is you can build an intermediate representation that fits the user's DAG, and then you just do Ray.remote, decorate that job on the fly, and run it as a Ray task. But you can promise your user, hey, if you decorate it with another framework, it's gonna run on another framework. This is very, very useful for early adoption. And the third, I think, from an infra perspective, I really want to focus on user experiences and minimizing the false positive rate is very, very important. For example, if I say your job is failing, then it better fail for a very good reason. If I say your job has been resubmitted, it better exist. Like it better not be fake. And of course, my team, we are heavy Ray users, and we also give back to community. I made some commits, but like those are too trivial. One thing is like because we upgrade very aggressively, we do find issues that like Kubernetes version break Kubernetes, and I think Ray team or any Scout team really do a good job of like following up and like shipping fixes. So I want to say shout out to them and to the Ray and open source maintainer community and Nscale, obviously. And that's my talk. And I will be around these 2 days. If you are interested in quant trading, systematic trading, just hit me up. Like we can grab coffee.